Quantitative Big Imaging, Lecture 10, Part 2. In this part of the lecture, I'm going to talk about software engineering, or some of the parts that you may have some use for, and in particular aiming at making repeatable workflows. I already mentioned this figure or showed this figure in Lecture 8, but then I was mainly focusing on no magic part, where I did the parameter tests to see which sensitivity different parameters had and so on. Now I'm going to go more into the structured part of working with the image data. And one part is, of course, handling the data in a correct way, but very important is, as you will be writing some code to produce your analysis, is to make sure that your code is testable, meaning you should be able to actually confirm that it's doing what it's supposed to. And also tracking history. So every change you have done should somehow be registered or saved. And for larger projects, you can also check that it is reviewed. So it's not only you looking to the code. And finally, also very important is that the code is documented. So you can actually understand what you did, or maybe can hand it over to someone else. And a further step would be to also track bugs and new ideas with the help of an issue manager, which is provided by many of the repository toolboxes. So what you need to support a reproducible workflow is, first of all, that you use a repository which guarantees that your history is managed. The next step is to use automated tests, and that guarantees that each little part of your code is actually doing what it's supposed to. Finally, which is more for larger projects, is to use a build server that combines the repository and tests. So once you send something to the repository, then it's automatically also running the unit tests. And how you should organize your code. Typically, we have until now mainly been using notebooks. To some degree also some Python scripts, but notebooks are not good for structuring and maintenance of the code. Also, they are not so easy to work with in a repository, and also less portable, and it's not so easy to share. And testing, I will show some examples how to do tests in notebooks, but in a larger context, it's not so easy to test notebooks. So notebooks, they're really great for the prototyping, but well, if you want to do something that has longer term use or maybe even shared use, then you should maybe go for a more sustainable solution where you produce small library functions. So in that, you can create small Python files or .py files which can be imported. So for example, let's say I had a set of functions and I saved them in mylib.py. Then you can import them in your Python script or your notebook using import mylib. And when you use the function, then you can use mylib.myfunction and some arguments, whatever that would be. Now, when you're running in a notebook, you import your function once, and then the notebook only notes what you imported. And if you now would do some editing on your code, then you have to either restart the notebook, run it from the beginning. It's not sufficient just to run the import function as up here once more, but you really have to restart the notebook. A way to get around that is to use the import lib, and then you can call the function import lib dot reload, and then tell which library you want to reload. And then you save yourself the problems of restarting the notebook, which means you have to rerun all the functions all the way down to where you need the function. Documentation is something that is not very popular to do. However, it's very useful. Just imagine you wrote some lines of code some months ago. When you look at the code next time, say tomorrow, do you actually remember what you did or what each argument has as purpose? Not to 100%, I believe. So it's important that you at least describe what your function is about and what arguments have for purpose, and also what the function is supposed to return. So that would be, in principle, the so-called API documentation. And what you also can do, it's more helping you during the development, or if you want to revise the code, is to have in-code comments. But don't clutter your code with comments, because then it's becoming unreadable. On the higher level, you can also do a user documentation that describes how the code is intended to be used, but that is only relevant if you are planning to share the code on a larger scale. But if you write it, it's always good. So my message is that the API documentation is a minimum. If you add other documentation, it's great. So an example of what the API documentation can look like, it's usually done with the docstrings in Python. And docstring is started by 3 hyphens like this. And then comes a text description, followed by a parameter description, and finally the expected return values. Good is also to tell which data type you're going to use. So if you call help on this function now, it reports this text here. So it's in principle all what you wrote. So that's great. That is for Python, how you do it. Then there are also other languages which you want to document, and one example how you can do it is working with a package called Doxygen, and then you can mark up your code and your functions in a way that you can compile a documentation of your code. I also said that testing your code is important to make sure that it does what it's supposed to. And in computer programming, this testing is often referred to as unit testing, and then you break down your code into smaller units that can be tested with a very trivial interface, ideally. And unit testing is actually provided in every language. So to some degree, sometimes it's integrated in the language. In other cases, you have to use an extra library to maintain or to support the unit testing. There are also a couple of good reading here. These 2 papers, actually the first one is a paper and the second one is just a link to a web page, but they give you good ideas how to design and why you need to do your unit tests. So the question is what you want to test, and there are different ways how you can do it, but in principle the idea is that each part should be tested independently, so that's why it's called unit testing. And if all tests are well, then you can change things and everything can be tested independently. And it's also much easier to do some upgrading, changing, because if you change something in one corner and that has an effect on something in another part of the code, that part will complain if your new function doesn't provide the right answer. So you can see system-wide or library-wide which functions are working and not working and what the consequences are. And ideally, you should test the entire path, but the entire path can also be tested. That means you are integrating, actually testing how different parts work together. So that would be the glue test. And how to test? There are different approaches. One is the happy path. So then you provide data to your functions in the testing framework and check if the output is what you want. Then there is also the option of provoking your code. That means you provide out of range data, things that may crash your code normally, and then you want to see if it responds in a good way. Test data is something you also need. Sometimes if you just work with scalars, it's quite easy, but you can also work with test images, and sometimes you can also use simulated data or model data. But you need to know what is the input and what is the expected output in order to do this test. And testing is only as good as your tests you define and how many tests you do. So if you test only 10% of your whole code, it's good that you test it, but you cannot rely on a stable system if you only have 10% tested. So an example of a unit test, this is Python function. I don't write it out here, it's not necessary. But the idea of this function is it should count the number of non-zero voxels in an image. And the tests that I have defined for it is first testing if a 2D image is empty. And this assert command is part of the testing. So what it says is test if this is true. And if it's true, then it's happy. And if it's not true, then it reports that you had a problem with this use case. And then we go on. We have empty 3D, then we have a three-dimensional zero matrix, and it also reports 0. And finally, there is also a little test here, test diagonal 2D. And then I create this I matrix, and then you should sum up to 3. And if all these tests are running okay, then your code is doing what it's supposed to. And as you can see here, these tests are very short and simple. And that's actually also the idea behind the unit test, that you shouldn't have too heavy tests because it takes long time and you want to run them very often in your development. And if you have unit tests that run 1 minute per test, then you are probably likely not to use the unit tests as often as would make sense. So keep them small and efficient, and you will actually use them afterward. So let's look at a testing example. We have this shape analysis. I think we had that as an example earlier, where we have a global function called shape analysis, which takes an image, and that one calls component labeling. We have analyze object, which can actually call a lot of other functions, and count voxels. We have calculate center of volume, shape T, orientation, anisotropy, and each of these functions can be unit tested. So on the first level, I would say we would take all the leaves of this tree, so this one and all the 5 down here. And then we have an integration testing or glue testing would be to call analyze object. And finally, the full glue would be to try shape analysis on the whole. So ideally, we should test on very many levels, and that would give you a good outcome for for your code. In Python, we have different frameworks. So there is a built-in Python module, which is called unit test. And it has a quite simple interface and it's easy to work with. So many beginners start to use it. If you get into larger code bases, then it's typical that people start using PyTest instead. And then you start to make a set of different tests for each module, and then you can run these every time this project is updated. So an example, for example, in Scikit-Image, they do it also, running unit tests. So here we have different examples. So here you can just click on these. You can see how they test. And here is the initial part of that. And well, it's a lot of code to begin with. We have test watershed 01. And here you can see a very small image. It's a lot of zeros, and then we have a region here in the middle. And for that, we want some markers. So we have a marker here in this region, and we are supposed to get something out from that. And then we have the expected, and then we compute the difference between expected and out from the watershed segmentation. And if the error is less than some epsilon, then we are good. Another one is also that you can do doc tests. So actually the tests are part of the comment or the doc string. So here is apply hysteresis threshold. And here you first get the description of the function, and then you get some return information. And then when we come to the examples, here you see these triple marks where you first define an image. So that shows that this is input, and then we run the thresholding, and the output from that comes out without these brackets, and that should be an array like this. And the doc test actually sees that this is code to execute, this as well, and this is the expected output. And the doc test then tells if you get that. And then comes, of course, the function below. And in Jupyter, you can also actually include it, but you need to do a little bit more. So we have the doc test part, which we had before, and then you need to import some func tools. And this is a decorator function, which I will show soon. And the decorator is used something like you have here. We have the auto test, and then you call this. You write it as add auto test, and then comes your function definition. And that would be an alternative to just write auto test my function, but then you can't really define the function. So with this way of writing, we can define a little test function. So we add this auto test, and the function is add5. And the test, you can see here, this is to be executed. So add5 with input 5 should give a 10. And when we execute this cell, it tells trying to add. So this is when it executes the test. And then you have the input, and it expects 10, and we got 10, so we are fine. So this is also a way how you can define tests and make sure that they are doing what they're supposed to. And if we look at a labeling function, so here we have auto test. Again, we use this decorator, and we create some test data. In this, again, the diagonal of ones. And we want to label it, and the output is like this. So we have only one object in the image, which is expected. Now we split the diagonal by setting the middle one as 0. That means we have two objects, and then we run the simple label again, and then we can see the expected output should be 1 and 2, so we should have 2 objects. And when we execute this, we can see, okay, trying to create, that worked, didn't expect anything from it, trying test image and expecting this array, that's fine. And then we try simple label, and the output that is expected would be the diagonal, and it's okay. And finally, we run it on this second type of image, and we can see that it's also okay. So you can write it like this, but in my opinion, it's a bit cluttered, and also it's when you run it in a notebook. When you do it in a Python file that you import, I think it's better to write a separate test file or test source code. In MATLAB, you can also do, it's documented in this MATLAB unit test framework. In C++, there are several different testing frameworks, and you can use Google Test. I think that is the most popular. There is also Boost Test, and Qtest is a test framework related to the Qt GUI interface. And all these can be run through the C-test environment, and that is provided with the CMake, which if you work with C++, you probably know about these two already. And driving this one step further is to do test-driven programming, and that's an approach where the program writes the tests before they write the functional code, which may seem a bit awkward, but in the end, you can see it as a task list. Once the tests are running as they are supposed to, you have solved your task. And with that, you can also easily estimate how far you have gotten, because you can see how many tests you have passed in your code. So you can also define what is the idea of the system, and for example, shape analysis should give an anisotropy of 0 when we have a sphere. That would be a test. Analysis should give the center of volume within half a pixel, or shape analysis should run on 1000 by 1000 image within 30 seconds. So that are the demands on your code, or that you can set up in your test. And another thing, which actually now the order is not the right one, but using repositories is actually a way to manage your code. And in principle, it's a database or backup system which is tailored to the needs of what you need as a software developer. And what it does, it synchronizes multiple versions. So if you're working on several computers, maybe different operating systems, or you work together with someone, you are likely to have different versions on different computers. And to be able to actually synchronize these, we have the repository that helps you, because it does automatic merging. And you can also work with branches. So that is side tracks of your development, so you don't destroy what you have been working with before. And very important is that these repositories, they are located on a centralized server. And now you ask, okay, this sounds quite a lot to work with, and why should I do it? So one thing is, it's easy to get back into earlier versions. So if someone, for example, asks, yeah, you wrote this and this in your paper, and how come is it like that? And you need to rerun your code. And meanwhile, it's 2-3 months ago, and you have been very creative and done a lot of things to your code. So now is the question, to answer that question you got, you may have to go back to what you did before. And this is where the repository is actually helping you. So it helps you to reproduce your results, and also, again, being very creative means you may introduce a bug here and there, and finding these is much easier when you do have it in a repository and have the history, because then you know, okay, this thing changed at some point, and then you can go back and compare in your history and see, that was the point, and then you can backtrace and fix the bug. And of course, if you're many people working together, then you can work on the exact same code base without disturbing each other, which is also quite a good benefit. The basic operations you have in a repository are, to begin with, you have add and commit. So add is just adding a file, saying this one will be considered as part of the repository. And when you commit, then you say, now this file has been tagged as uploaded, and I have a status that I can track back to. So this is the commit is actually the history part of your code. Push and pull is the communication with the server. So if you push, you send things to the server, and pull is when you get things from the server. So, and then of course you can work with branches. So then you have to be able to create, switch and merge branches. And these are the basic operations you can work with within a repository. There are also different repository frameworks. The one that today is used a lot, in particular in academia and also in open source development, is Git. Then Microsoft has provided the Azure framework. Older frameworks are Subversion and CVS, but they are really about to phase out these days. The plot shows up to 21 how different repositories were in popularity. So you can see that Git is very popular. Azure is coming. I believe it's also mainly coming because Windows is the main, or Microsoft is the main development platform for many. And if you use their tools, then it's more likely that you actually use the repository services that they provide. A different comment is also actually that one of the most popular Git repositories is GitHub, and that's actually also Microsoft owned, so there is a bit overlap there. And there are also different Git servers, so there are many servers available, and they don't only provide the repository, but they also provide issue tracking, so you can submit trouble tickets. And issues and trouble sound a bit negative, but you can actually also use it as kind of a reminder list. So if you have new ideas, you submit an issue, and then you can write down what you wanted to do. Another thing that is also often provide is project management. So within different versioning, you can actually say which issues you want to handle during a certain time between two versions or something, and that can help you using so-called Kanban tables, for example. There are different servers available. So publicly, you have quite many. There is GitHub, which I already mentioned. There is also GitLab, Bitbucket, and Gitea is an open source version of GitHub. And yeah, there are different services out there. Locally, you can go to ETH, has a general GitLab, and there are probably also departments which maintain their own Git servers. And at the Paul Scherrer Institute, where I'm working, we have just recently got the Gitea repository, which is also open. So you can define how you want to work with your repositories there. And the workflow when you work with the repository is you can, of course, work with single branch. Then it's more like an advanced backup server with comments, and you can go back in history. But it's actually much better to work with multiple branches. And there you can see, so what you can see in the figure here is a snapshot from my repository. And here you have the black one is the main branch, and depending on different issues, I have then several branches. You can see here that I have a branches starting here, and I synchronize them and merging them back into each other and so on. So you can see the workflow in these branches is that solving an idea, a bug or something out in a branch. And once you're sure that it's actually doing what it's supposed to, then you merge it back into the main branch. And ideally, you should never commit anything to the main branch unless you have tested it and also, if possible, reviewed it. Meanwhile, GitHub, for example, provides even an AI reviewer that go through your code and see what you actually did. Sometimes it even comments that this may or may not be a good idea to change, can find some typos, etc. But it's usually better to have a human to review the code. And once you have set up your work in repository, you can also start doing continuous integration or CI. And there are many packages out there. Meanwhile, even the repository services also provide continuous integration. And that is that once you push a piece of code up to the repository, this code is automatically tested and the unit tests are run. And right now, I'm mainly in my projects using the GitHub's own build actions. And the advantage of this is that you don't have to care much more about running the tests on 5 different operating systems, etc. It's a big project. But it's actually happening in the background. So you just push and it happens. And that is actually a good advantage. You don't have to have your own computers set up for it, but it's solved remotely. So in principle, all larger projects, they run in some kind of CI, and there is a good reason for it. So what you can see here in this figure is that there was first something was committed and that was run okay, and then we did some changes and these crashed in this case, and quickly we had to fix something so that it was actually running good again. So you can really see in the reporting what is going on. Now I will actually switch off from the lecture and actually round off this lecture, and I will record a separate session where I demonstrate how to work with Git. So again, today's lecture ends in principle here, but stay tuned for the demonstration. Today I talked about multiple modalities and some ideas how to work with this multimodal data. And now in this part, I also showed you some tricks of the trade when we work with software. Important is that you should work with repositories, document your code, run unit tests, and if you have a large project, it can also make sense to work with continuous integration. Thank you for listening.